Welcome to today's webinar. My name is Stephen Wu. I'm a fellow and distinguished inventor here at Rambus Incorporated, and today I'm going to be talking about memory systems for AI and leading-edge applications. Well, there's certainly been a lot of interest and a lot of news in the industry about AI and a lot of chips that are being built specifically for this market. And it's really interesting, the question of why is it that AI has suddenly taken off? It turns out that many of the techniques which are in use today in modern AI chips and applications have actually been around for several decades. But they didn't really take off during the last wave of interest between the 1980s and the 1990s. And the question is why? Well, if we take a look here in the chart at the left, you can actually see a bit of an explanation for why that is. Back in the 1980s and 1990s, processors were actually not fast enough and memory performance was not quite good enough to enable neural networks and modern techniques to displace conventional approaches. And in that time frame, the conventional approaches remained popular. But if you fast forward a few decades to today, Moore's law has provided us with about 5 orders of magnitude better processing power and about 3 to 4 orders of magnitude better memory performance and capacity. Those two things together now make it so that neural networks can outperform the conventional approaches, and neural networks have now become the method of choice for solving a lot of different problems. You couple that with the graphic that's shown on the right, and that's the growth of the world's digital data. And what you find is that by this and many other kind of studies, even by the most conservative estimates, the world's digital data is doubling about every 2 to 3 years. There's so much digital data in the world that AI is almost the only way now to begin to make sense of it all in a timely fashion. And there's a dependence that's forming. Having so much more digital data helps us train our neural networks and make them even better. So this dependence, which is tightening, the need to use AI to interpret the data, and the wealth of data that's available to make AI better is tightening, and we believe it will continue into the future. But most everyone agrees that with this current wave of AI, that we're really just at the beginning. There's much more left to do. People would like to do more sophisticated algorithms, larger data sets, and other methods and applications. But what's really challenging is, although everyone's calling for more performance, the question is really how to get there. It turns out that two of the tools that our industry has been relying on for the past several decades, Moore's law and power scaling or Dennard scaling, it turns out that Moore's law is slowing and power scaling has stopped. So the question to our industry is, just at the time we need them most to get better performance and better power efficiency, how will our industry continue to provide those things when two of the most important tools that we relied on over the past couple decades are no longer available to us or are slowing down? Now, coupled with these challenges are actual challenges that are going on to the internet architecture itself. We're all familiar with the cloud-based model where we have endpoints like our phones. They capture data and transmit that data up into the cloud where the cloud processes the data and interprets it and sends some actions back to things like our phone that can tell us to do things like navigate or things like that. The upcoming rollout of 5G infrastructure is going to enable processing now in a new location, and that's at the edge. And so in addition to being able to do some processing in the endpoints in the cloud, we're going to have another location, the edge, which will change the dynamic. The other thing that's very interesting about the edge is that because we're capturing so much data, as I showed you in the graph on the previous slide, you really can't move all that data up into the cloud. The growth of the world's digital data is really faster than the speed at which networks are improving. And so really, you can't move that data very far. And the question is, what do you do if you need to process it? Well, the edge provides some of that answer, the ability to move the data just a very short distance to other compute locations that are geographically distributed and closer to the endpoints helps improve performance as well as power efficiency. The cloud will still be there, and what we expect is that the cloud will be used for some of the toughest interpretation tasks and the toughest analysis tasks. So when data is captured by the endpoints, it'll be sent to the edge where it could potentially be partially processed. And a smaller amount of higher value results could then be pushed up into the cloud, preserving network bandwidth. In terms of AI, we expect to see AI deployed in each of these locations, but the needs and the way AI is implemented we expect will be a little bit different in each location. In the cloud, we expect to have the highest performance solutions. And in terms of memory, they're going to need the highest performance, lowest power solutions to support training as well as inferencing. The solutions of choice that we expect to see are on-chip memory, as well as very high performance solutions like HBM and GDDR. At the endpoints, really, these are still going to mostly be battery-powered devices. And much of what we see today, where they're typically used for inferencing, is going to be true in the future. What will be needed is low-power inferencing, and so the memory types we expect to see to support that are again going to be on-chip memory as well as low-power mobile memories. The edge is going to be a very interesting opportunity. The edge itself is really bifurcating in its definition. So now people talk about the near edge and the far edge, and near edge being closer to the cloud and the far edge being closer to the endpoints. We expect to see the full range of solutions there in the edge. So in the near edge, when you're closer to the cloud, we would expect to see solutions and memory systems that look a little bit more like what you see in the cloud, things like on-chip memory, HBM, and GDDR. And in the endpoints, we would expect to see the things that you would tend to see more in the endpoint devices. And so at the far edge, they'll pick up those kinds of memory solutions, things like LPDDR, and we'll even expect to see some DDR in those solutions. Well, let's take a closer look now and see if we can understand how and when particular architectures are limited more by their compute performance or more by their memory bandwidth. What I'm going to show you is a modern computer architecture tool called a Roofline Model. And the Roofline Model helps us understand when particular architectures are limited more by their compute resources or more by their memory systems, and in particular, the amount of memory bandwidth they're able to provide. What a Roofline plots on the y-axis is performance, the total number of operations you can do per second, against the x-axis, which is something called operational intensity. And it's just a measure of how many times each piece of data is reused for a computation once it's brought in from the memory system. If it has a high operational intensity, it means that that data is reused many, many times in calculations once it's brought in from the memory system. Now the roofline is composed actually of two different lines. The first line is a horizontal line, and that's the peak performance of the processor. So if every compute unit is running at full speed all the time, you'll get some peak performance that you can't exceed. The other part of the roofline is a slanted part of the line, and that part of the line shows you when the architecture is limited by the amount of memory bandwidth that you can provide. If you can't provide enough memory bandwidth, then you actually achieve a lower performance than the peak performance. The roofline itself is actually colored in solid green here, and it's part of the sloped part of the line and part of the flat part of the line. Now, each architecture has its own roofline model owing to the fact that they each have different peak performances and different memory system bandwidths that they can provide. What we can do is we can plot different applications on a roofline curve and understand for a particular architecture whether that application is limited more by memory bandwidth or more by the peak compute performance of that processor. In this particular case, application number 1 lies more underneath the slanted part of the line. What that means is the operational intensity, or the number of times each piece of data is reused in that application, is low enough that we're not able to achieve peak performance. If I was able to provide more memory bandwidth, I would be able to get much closer to the peak performance. On the right there is application number 3, and what you see is that that lies more underneath the flat part of the curve. What that means is application number 3 actually has enough memory bandwidth, and it's limited more by the number of compute resources that are available in that processor. If we had more compute resources, either more adders and multipliers, or perhaps could run them faster, then we could achieve a higher level of performance. And application number 2 is kind of near where both of those lines meet. And what that means is it's limited in part by the peak performance and the computational resources of the processor, and in part by the memory bandwidth. If you're able to provide more of both, then application 2 could benefit. One other interesting point on the roofline is that corner there called the ridge point. And what that is it's really the minimum amount of reuse, the minimum operational intensity you need to achieve the maximum performance in the processor. It's an important point because it helps us understand what applications have to do in terms of how their algorithms are arranged in order to achieve peak performance. Now, the central question here is, given that we have this nice tool for helping us analyze compute and memory system limitations, how are AI applications performing as hardware evolves? Are they more compute limited, or are they more memory bandwidth limited? This graph comes from a paper that Google published a couple of years ago that discussed their first generation tensor processing unit, or TPU. It's a very insightful paper. What they did was they compared the performance of the Google TPU against 2 other processors. And you can see 3 different roof lines here, one in red, one in gold, and one in blue. The blue roof line represents the Google TPU, a special purpose-built piece of silicon that was designed to do AI inferencing very well. In red is the NVIDIA K80. It's really more of a graphics processor that's designed to do a larger class of operations very well. And then finally in gold is the roof line for the Intel Haswell CPU, a very general purpose processor. And what's interesting is, in this study, 6 different types of neural networks were coded for each of these different architectures. The stars show those architectures of neural networks that were coded for the Google TPU. The triangles are those same neural network architectures coded for the NVIDIA K80, and the circles are those same neural network architectures coded for the Intel Haswell processor. And what you find when you look at these neural networks running on Intel Haswell and the NVIDIA K80, so the circles and the triangles, you'll find that many of them are under the flat part of the respective roof lines, and many of them are under the slanted part of those roof lines, which means some of these neural networks are limited by memory bandwidth, and some of them are limited more by compute performance. But when you go take a look at the stars, what you find is that the vast majority of them lie on or under the sloped part of the roof line for the Google TPU. And what that tells us is that memory bandwidth is an important bottleneck for these purpose-built AI processors. And it's part of the reason why when Google eventually went to later versions of the TPU, they used the highest bandwidth memory available at the time, which was Hbm memory. And what we can infer from all of this is that memory bandwidth is critical for AI applications. And we need to not only provide as much as we can, but we have to make the most use and the best use of that bandwidth that's available to us. Memory bandwidth is a very important resource for AI chips, and it's very important to make the best use of the available bandwidth. Many times, calculations are done as 32-bit floating point numbers, but a lot of research has been done in the case of AI showing that that level of precision isn't really needed to get good performance. It turns out that many architectures use reduced precision. So instead of doing all calculations with 32-bit numbers, sometimes 16-bit, 8-bit, or even fewer bits are used. Now the benefit of doing something like this is that the available bandwidth you have, you can actually squeeze in more numbers because each number now takes fewer bits to encode. What this slide shows here is it shows for an FPGA implementation that was done by Microsoft, you can actually see for various types of precision, 16-bit integers all the way to a kind of a special implementation of 8-bit floating point, you can actually see that the performance of the neural networks rises pretty dramatically with a newer FPGA, the Stratix 10. And so what this study helped prove was that using reduced precision could get you much higher performance. And there's another part of that study showed that the accuracy of these neural networks didn't suffer at all. And so the benefit of being able to use reduced precision without having the accuracy suffer is that you can now make better use of the available memory bandwidth, either to run larger models or to run your models more quickly. Well, let's take a closer look at some common memory systems that are used in the highest performance AI applications. On this slide, we see on-chip memory, high bandwidth memory, and GDDR. On-chip memory in the form of SRAM is by far the highest bandwidth and most power efficient solution available today. Today, you can get on the order of tens of terabytes a second of memory bandwidth using on-chip memory. And you get by far the best power efficiency. But the trade-off here is that the capacity is fairly low. Today you can get on the order of a few hundred megabytes of total capacity. If you're running smaller neural networks, or you're able to split your neural network between multiple chips and they can work together, then on-chip memory is a great solution. But if you're not able to do that, then you have to use external memory. And so the two external memories of choice are high bandwidth memory and GDDR. High bandwidth memory, shown in the middle, is a new kind of memory technology, and it involves stacking. The memory devices themselves have multiple die in that stack. Several die hold the DRAM bits, and there's an additional die called the base layer, and that interfaces between the DRAM bits and the SoC. HBM devices are also different because they have a lot of data wires that run at a relatively low data rate. Each HBM stack has 1,024 data wires running at 2 gigabits per second. That's more wires than can really be supported on a standard PCB. And so the DRAM device is connected to the SoC using a silicon interposer, where those 1,024 wires are actually etched in the same way that wires are etched into an SoC. Now, being able to have a bunch of fine pitch wires etched into a silicon interposer, again, allows us to have a very wide I/O interface running at a very low data rate and still achieve a very high bandwidth simply through sheer numbers. What you can achieve with HBM memory is very high bandwidths, not quite as high as with on-chip memory, but you get very good capacity in return, and by far it's the best bandwidth for any external memory option that's available. And you see that it's used today in solutions from the graphics card makers as well as from some of the AI chip vendors as well. And on the right is GDDR memory. So GDDR memory was originally created for the graphics market 20 years ago. And it's had several evolutions, and so the current generation is GDDR6 memory. It's a great trade-off between bandwidth and power efficiency, cost and reliability. It doesn't have any stacking that's involved. It doesn't require any new kinds of technologies, and so it doesn't really have the same kind of cost implications and the same kind of difficulty with implementation that HBM does. But it doesn't quite have the same level of performance or power efficiency either. And so it's a bit of a trade-off, but the benefit is it relies on much better understood manufacturing techniques and a base of knowledge that's been around for a couple of decades. And GDDR memory has traditionally been used in graphics cards, but is now seeing its way into solutions for AI. And so what we see on this chart is really we've got three different options that are best suited to different needs depending on what the needs of your system really are. Let's take a closer look at GDDR memory. And so if I wanted to build a 256 gigabyte per second memory system, how would I build that today with GDDR6? The way I would do it is shown on the upper left. I would have 4 GDDR6 DRAMs connected to my SoC. And each of those GDDR6 DRAMs has 32 data wires that connect into the SoC through a set of circuits called the PHY. And you can actually see on the lower left there is a side view picture of how the GDDR6 DRAM is connected to the processor and the PHY. All that happens is these parts are packaged in a standard way, and we just connect them through wires in a PCB, a very simple, well-understood kind of assembly and manufacturing flow, similar to things like DDR. Let's compare and contrast that with what we would have to do to build a memory system with the same bandwidth out of HBM2 memory. On the upper left here, you can see what a memory system for HBM2 looks like that achieves 256 gigabytes a second of memory bandwidth. Here we have a single HBM2 device connected to the SoC on an interposer. We have 1,024 wires that connects the DRAM to the SoC. And that very wide interface, like I mentioned before, is running at a lower data rate. And I can't connect those two chips together directly on the PCB. On the lower left here, you see the stack up, a side view of what it takes to connect the processor to the HBM stack and then to the rest of the system. The HBM DRAM stack is connected to the processor through the silicon interposer, which allows us to connect a large number of wires in a small area. But that interposer can't be mounted directly on the PCB. Instead, we need another substrate in between, and then that substrate can be put on top of the PCB. What we see here is that there's a small number of devices that are required to get to the same memory bandwidth, but it's a more complex manufacturing and stack-up. It requires additional components, the interposer and the substrate, and it also involves stacking within the DRAM device itself. So it's new manufacturing techniques and new assembly methods that are not as familiar to the industry. So this slide here compares our two solutions that I've shown in detail on the previous two slides. What we're showing here is for equal bandwidths, 256 gigabytes a second. Here's where the differences are between the technology. The primary differences are in things like the data rate. Again, GDDR6 is running each of the data wires at a much higher data rate because there's fewer data wires. So running at 16 gigabits per second as opposed to HBM2, which is running at 2 gigabits per second. The primary challenge here with GDDR6 is signal integrity. Being able to signal at a very high data rate across a PCB is a challenge, but it is possible to do, and if you can do it, it will lead to a lower cost solution, as I talked about before. We also take a look at those PHY circuits which connect the DRAMs to the SoC. You see something pretty interesting. In the case of GDDR6, the amount of area you need to reserve on the SoC is between 1.5 and 1.75 times the area you would need for the PHY circuits using HBM2. So there's an area advantage on the SoC to implementing HBM2. And in terms of power, it's a larger difference. The PHYs on a GDDR6 implementation are anywhere between 3.5 to 4.5 times as much power as the PHY for HBM2. So again, that's a power advantage for HBM2. But where the trade-off really occurs is in cost and complexity. HBM2 requires an additional interposer and a substrate, and it involves stacking in the memory. And those things add extra cost, and the fact that they're new also adds additional cost because there's not quite as much manufacturing experience associated with HBM2 just yet. So what we can see is it's really a trade-off between what you value more and what matters more in your system. If you can tolerate the cost and complexity of implementing with HBM2, then that's a very, very good solution. But if your system is one that requires either more standard manufacturing techniques or that can't quite tolerate the additional cost, then GDDR is a great solution. If we turn towards looking at the individual types of memories that I talked about, we can take a look a little bit more deeply at the benefits and challenges of each. On this slide here, I'm showing some of the benefits and challenges of on-chip memory. And on-chip memory is used today in some infrastructures like Microsoft's Brainwave and by companies like Graphcore who've developed their IPU chip. Again, one of the big benefits is it's got extremely high bandwidth. On the order of tens of terabytes a second are possible today with on-chip memory. It's also extremely high power efficiency. The data itself doesn't need to move very far. And so that's one of the big parts of why power is much better here. It's very low latency, again, because you're not moving the data very far. And it also achieves very high utilization without having to batch jobs together. And that's particularly important for certain types of cloud infrastructures. The challenges are that there is lower storage capacity compared to external DRAM. But people do implement some interesting techniques to save on some of that capacity. Sometimes, instead of saving intermediate results during more complex calculations, those results are just recalculated because it's cheaper and faster to do the recalculation than to store them and retrieve them from memory. The other issue that comes up is with the limited memory capacity, you do need a scalability story if you've got large models. And so on the bottom left here, you actually see a graphic which shows the Brainwave approach to system scalability by chaining together multiple of their FPGA cards to solve and to implement some of their larger networks. The primary benefits of HBM memory are that it achieves very high bandwidth, the highest bandwidth for any external memory device today, up to 256 gigabytes a second of bandwidth per HBM2 DRAM stack. It's also got very good power efficiency, and that's because it's running a large number of IOs, again 1,024, at a relatively low data rate, 2 gigabits per second. And you can see that there are a number of solutions, especially in the AI space, that are adopting HBM today, like the NVIDIA Tesla V100 and the Google TPU version 2. But some of the challenges for HBM are that it does have a high number of IOs, so it requires a silicon interposer to be able to place that many wires in close proximity to each other. There's additional cost and design complexity with all the stacking involved, both within the HBM DRAM stack, as well as stacking the components together on top of the interposer and the substrate before it goes onto the PCB. The system engineering challenges associated with this stacking and the complexity with trying to do things like cool that, as well as to maintain reliability, all add to the difficulty of implementing HBM2 solutions. Still, if it's something that you can tolerate in terms of the costs and the design complexity, HBM2 can be a great solution for you in terms of external bandwidth solutions. And finally, GDDR is shown on this slide. And so GDDR we find to be a very good kind of middle ground between performance, complexity, and cost. And so you can get very high bandwidths and high capacities because it's an external type of DRAM that's already packaged. It's easier to integrate, and the system engineering is much simpler compared to something like HBM. And so we find that for systems that are particularly cost sensitive, or that ones that where it's too difficult to implement HBM, GDDR is a great solution. The primary challenge for GDDR is running at very high data rates across the PCBs. Signal integrity becomes more difficult, but with well-designed and well-managed PHYs and packages and boards, we find that GDDR is actually very implementable at these speeds. And you see on the lower left there is kind of a screen capture and an eye diagram from some work we did a number of years ago proving out the ability to signal at these data rates across standard PCBs. And what we find is in the industry today, there's a lot of acceptance of the fact that these data rates can indeed be achieved over standard PCBs. So in summary, what we've talked about throughout this webinar is that AI really is driving a bit of a renaissance in computer architecture, and there's a wealth of new silicon being developed. It's an extremely exciting time to be in the semiconductor industry because of this resurgence in interest in new computer architectures, especially around AI. We find that memory bandwidth is a critical resource for AI applications, and memory systems have once again become a hot topic within the semiconductor industry. For the highest performance AI solutions, there's multiple options that are suited to different AI application needs. On-chip memory is the highest bandwidth and the most power efficient, but its capacity is a bit limited. Hbm memory gives you a great story for external memory. It's very high bandwidth and power efficient, but it's more challenging to implement, and there is more of a design complexity and hence more issues associated with implementation. And finally, GDDR memory, which has been around for a couple of decades, is a great trade-off between bandwidth, capacity, power efficiency, and cost, as well as reliability and design complexity. And it can be a great solution depending upon the needs of your system. Thank you very much for joining our webinar today. For more information, you can visit the links shown at the left side of this slide to learn more about artificial intelligence and machine learning, as well as some of the memory PHY solutions that we provide for some of the technologies I've talked about in this webinar. And if you have other questions, you can contact me directly at the contact information shown at the right.